And now we come to our third talk, which will be given by Dmitri Peresunko, yeah, and he will talk about direct photon production in proton-proton, proton-A, and AA collisions. Please share slides. You hear me, right?
Yes.
Very good.
I'm trying to share.
Very good. We see you.
Okay. First of all, I would like to thank organizers to give me opportunity to discuss open issues in direct photon production and discuss with experts in this field. First, I would like to introduce some definitions. So direct photons, which I will discuss, is photons which do not originate in the case of final hadrons, but occur in scattering of charged particles in hot matter. One can classify direct photons into prompt direct photons, which occur when two colliding nuclei or two protons penetrate through each other, and patterns of incoming nuclei interacts, and thermal direct photons when we have thermal emission from hot matter. Besides direct photons, one can consider isolated photons, which are similar but not the same. It is photons which have no hadronic activity in some cone around your photon. And the main part of photons in any collision is decay one, which is from decays of final hadrons, mainly pi0 and eta mesons. And to provide you some scale, we have thermal photons should have almost exponential spectrum, and if exist, should dominate at more or less low PT. Prompt photons will have parallel spectrum and have to dominate at high PT, and normal decay photons are much yield of decay photons much higher, and they dominated almost all PT. Okay, brief comparison of isolated and direct photons. So in experiment, direct photons are measured as a difference between total or inclusive photon yield in event minus number of decay photons, which is calculated from decays of measured hadrons. These direct photons cannot be measured in event-by-event basis and only in statistical subtraction. Isolated photons is main idea behind isolated photons is that we select photons which came from Compton scattering or annihilation, and such kind of photons will be single, while photons from Bremsstrahlung or fragmentation or decays of hadrons will be accompanied by other hadrons and will be rejected with such a cut when we require no hadrons in cone around photon. So isolated photons can be measured in event-by-event basis, but and as you can see in this plot on the left, almost all direct photons are isolated at high PT. So this is a ratio of isolated to direct or decay photons. So at high PT, almost all direct photons are isolated, so no difference between them. But at low PT, we have a larger and larger contribution of fragmentation and Bremsstrahlung. And as well, we have more and more photons which came from decays and still pass isolation criteria. So in reality, it is not possible to go to very low PT. So at the PHENIX or at RIC energies, it's one cannot go below 5 GeV. At LHC energy cannot go below 10 GeV. So there is some similarity and difference between direct and isolated photons. Okay, to look at the direct photons in heavy and proton nuclear collisions, we first need to some baseline, and let's first compare direct photon yield in proton-proton collisions at different energies. So in late 90s, some techniques were developed by these two gentlemen who managed to to reproduce direct photon yields in PP collisions, and it was implemented in JetFox package. And with this package, it was Polarange was able to reproduce direct photon spectra in almost all available data at this date, except a few experiments which contradict to others. And as you can see, and description of data is pretty good, and we can reproduce them with accuracy about 10–20%. Okay, when LHC started, we can test direct photon on, in this case, isolated direct photon production at high energies. So this is a results summary of results of 3 LHC experiments. And you see that agreement between measured isolated photon yield and QCD predictions is pretty good in all 3 experiments, and in very large PT range from 10 GeV to a few TeV. Okay, this was high PT end of our spectrum, and at low PT end we can look at direct photons, and again it was measured at RIC energy by a PHENIX experiment, and it was compared by QCD predictions, and you see that these calculations reproduce direct photon yield in PP collisions pretty good. The same situation right in LHC energies measured with ALICE. You see where we have measurements data, or QCD predictions reproduce data pretty well. Okay, so we have a good baseline and can try to understand what happens when we go to more complicated collisions. And let's look at start from small collisions, small systems. It is proton nuclear ones. So again, we measure direct photons in proton collisions at the same energy, parameterize it, and then measure direct photon spectrum in proton gold collisions and compare it to this parameterization scaled by expected number of nuclear collisions in this proton gold. And you see that at high PT, this expected yield agrees with measurement, while at lower PT there is some excess. Okay, and it is better to estimate or quantify the success looking at the ratio, which is a RP gold, which is a ratio of spectrum measured in proton gold collisions divided by spectrum measured in PP collisions and scaled with the number of expected nuclear collisions. So if we do not select events according to multiplicity, this ratio is consistent with unity. But if we select most events with the highest multiplicity, this is 0 to 5% of events with highest multiplicity, we see a strong excess of number of measured direct photons. Okay, this can be interpreted in several ways. One of them is that even in these collisions of proton with nuclei, some hot matter is created and it emits thermal photons. And this was put in this hydrodynamic calculations, which shown in this blue curve on these 2 plots. And you see that this idea of small portion of thermal matter more or less reproduce data within uncertainties. Okay, this was RIC energy, 200 GeV per nucleon. And if you go to LHC energies, it is proton-lead collisions at 200 or 2 TeV per nucleon. ALICE measured ratio, which is number of inclusive photons over number of decays, and excess over unity means presence of direct photons. But unfortunately, uncertainties are still large, and we cannot resolve a situation when we have no significant excess, which would be mean, okay, R gamma equal to unity, or these predictions of same hydrodynamic model, which shown with green line, which predicts about 5 or few percent of thermal photons. So it would be interesting to understand what is the reason of this excess of OPT direct photons, even in such as small systems, whether it should be attributed to thermal emission of hot matter created in such collisions, or we just biased towards some special processes which produce a higher number of final hadrons, but as well produce higher Bremsstrahlung photons and so on. And important questions: is there any possibility to disentangle these two scenario? This was my first question. Now we can go to direct photon spectrum in AA collisions. And again, we can start from RIC energies. And now we can look at the direct photon spectrum in go-on-go collisions at 200 GeV and compare it to what we expect to expected prompt photon contribution, which is calculated by scaling of PP collisions with number of expected nucleon collisions. So this band is expected from photon contribution. And you see that at high PT starting from 4 GeV in all classes of centrality, so left is most central, then mid-central, and most peripheral. This prompt photon contributions agrees with high PT, with measurement, but at low PT we have excess, which we can now interpret as a thermal photon emission. And this excess is rather strong, as this factor of 10 approximately, and slightly depends on centrality. Okay, as expected, it's slightly somewhat reduced, but is not zero even at very peripheral collisions. Okay, let's try to describe this with some theoretical models. And the simplest or most straightforward is a hydrodynamic model. And the main idea of it is that we integrate thermal photon spectrum or thermal photon emission rate over the space-time volume occupied by hot matter. So to do this, we need emission rate, which depends on photon energy, temperature, baryon chemical, maybe other chemical potentials, and for velocity of elementary volume and the evolution of or description of distribution of temperatures, chemical potentials, and flow pattern is provided by our hydrodynamic model. Okay, then we can introduce some complications, very different equations of state, initial conditions, apply equilibrium or non-equilibrium emission rates, and so on. But main idea is this. And concerning this photon emission rates, it is related to the photon self-energy, and it was calculated a long time ago for hadronic gas and for quark-gluon plasma in this by these two papers. Then it was zero extension to non-equilibrium case, but this is more or less basic parameterization which is used in most of hydrodynamic models. So, but these calculations are done in for matter far from transition region and far from critical point. So question appears: what is what happens with photon emission rate when matter goes closer to transition region? Whether it should increase as any other susceptibility. And it is important because mean free path of photons is about 100 times larger than typical sizes of the fireball. So photon emission is not saturated, and it will proportionally increase if emission rate will increase if system goes closer to to the critical point. So my second question to the community, whether we can estimate what happens with emission rate when we get closer to critical point, and okay, and how to and then we can make some quantitative estimate what happens with direct photon yield when we when system goes closer to critical point during its evolution. Okay, with this hydrodynamic model we can try to reproduce measured spectra, and this plot shows attempts of several groups to reproduce direct photon yield measured in central gold collisions at weak energy. And you see that these predictions cover a rather wide range of possible yields, and main three parameters here is the initial time and related to it initial temperature. As we have hydrodynamic evolution fixed at the final stage, reproduce it to reproduce spectra of final hadrons, spectra and use of final hadrons, we have no strong argument to which initial time we should fix, and so far we can extend our start of our hydrodynamic evolution to lower and lower times, depending on some speculations and our belief how fast our system comes to the local thermal equilibrium. So this is a big question to all hydro calculations, how to choose what is the initial starting time of the evolution and how to fix it. Okay, we have a lot of different hydrodynamic calculations of yield of direct photons, but most of them, if they are fixed to reproduce final hadron yields, flow, and so on, spectra, the all of these calculations tend to underpredict direct photon yield. So this is two typical examples. Left is calculations from this Gale, Paquet, and company, and for go collisions, and you see that predicted direct photon yield underpredict measured one by a factor of approximately 5 in this case. Similar happens if you go from hydro to transport model, is like a PHSD. So you see this rate is a sum of all contributions, and as well it underpredicts measured direct photon yield at low PT by approximately factor of 2, and this is valid for all considered centralities. So if you go to LHC energies, again we have measurement from Alice of in lead collisions at 276 TeV per nucleon, and again we have comparison with hydrodynamic models and with PHSD model, which is marked by Linick et al. And again for central collisions, models underpredict direct photon yield in soft PT by a factor of 2 to 5 depending on the model. So question appears, what do we miss some important source of direct photons, or do we somehow underestimate emission rates both from quark-gluon plasma and from hadronic gas, and how to solve this discrepancy. How can we solve this discrepancy? Okay, a side remark. If you go not to higher energies but to lower and consider an AA collisions at SPS, so it is W98 square root 17.3, and even go to even lower energies to Nika in 10 GeV per nucleon and 5 GeV per nucleon, we find interesting situation that a prompt photon or expected contribution from prompt photons is do not dominate anymore at high PT. And if you go to low and low energies, the PQCT contributions, which is shown with green band here, is appears to be smaller than expected thermal photon contribution calculated from this hydro model. And okay, even more dramatic at 5 TeV. And this opens a very interesting possibility to explore high PT end of quark and hadron distribution in a hot matter, which will define this high PT end of our thermal photon yield. Of course, such a straightforward application of integration of emission rate with hydrodynamics is not correct, because okay, it assumes that this matter is in equilibrium and remains in equilibrium for infinite time, so that all tails of this Boltzmann distribution was managed to build, and in reality it will not happen. And with such collisions, we will be able to look how fast these tails will be built in such collisions, and okay, looking at direct photon, thermal direct photon yield at high PT. Okay. Recently, PHENIX produced a very interesting scaling. So they calculated a number of direct photon yield, or overall PT integrated direct photon yield versus charged particle multiplicity. So this is a total number of direct photons with PT above 1 GeV in left port and with PT above 5 GeV in right port, and versus charged particle multiplicity. This means, okay, charged particle multiplicity defines your total volume occupied by your system, and to some extent lifetime of your system. And they found that if they plot all direct photon yields measured versus in different kind of collisions, they found a pretty nice scaling with power parameter 125. And what is surprising, that even a small system like okay, proton nuclei and deuteron gold and cuprum collisions, they all follow the same trend, which is very surprising. But caveat of this measurement is that if we include in this comparison two other experiments, that is W98 points, which is hardly seen in this right port, and point of a star experiment, which is not shown in this plot, but which predicts the direct photon yield 5 times more than measured by PHENIX, we find breaking of this scaling, and so there is a good question why two experiments which can be compared to the PHENIX in the same charged particle density region do not coincide with these measurements and do not fall into this trend. Okay, and the last part of my talk is a direct photon puzzle. So direct photon collective flow is collector expansion of a hot fireball, which transform initial asymmetry of in space to the asymmetry in momentum. And it is characterized by expansion in Fourier series, and we will be interested in several first variables, which and elliptic flow and triangle flow in this case. So as you can imagine, as direct photons are emitted in all stages of the collision, and most direct photon yield is proportional to the temperature in the force. So one can expect that mostly direct photons or several direct photons will be emitted at the very first stages of the collision, when collective flow still is not yet developed. And this is illustrated in hydrodynamic calculations shown on the right part, when different contributions of from thermal photons from coagulon plasma and from hadronic gas, and combination of them is shown. And you see that indeed collective flow of thermal photons emitted from coagulon plasma is much smaller than collective flow of hadronic gas. And if you start later and later, so your colors correspond to different times when you start your hydrodynamic expansion. So if you start later, you have a small contribution of coagulon plasma, and you see larger and larger final flow of direct photons. Okay, but when this quantity was first measured, it was found that direct photon flow is comparable to the flow of final hadrons. So this is shown on the right plot, where we have flow of final hadrons or final pi zero, which is shown with black points, and red is the flow of decay photons which originate from these pi zeros, and on the right is the flow of direct photons which have large uncertainties and comparable to the flow of final hadrons. And so we observe this more or less the same situation for all centrality classes, from mid-bias to central and mid-central collisions. Later, it was accuracy of this measurement was improved, and several other methods of direct photon measurement was tested, but they all agree pretty well with each other, and they all produce or show very large flow of direct photons. The same situation happened at LHC. So Alice measured direct flow of direct photons in central and mid-central collisions. So direct photons are shown with points, and decay photons are shown with this band. And you see that direct photon flow and decay photon flow are pretty well agree with each other for relatively low PT, and and direct photon flow became smaller and smaller when we go to high PT, where we have larger contribution from prompt photons which do not carry any flow at all. And for comparison, we have here several hydrodynamic predictions and transport model from PHSD transport model, and you see that all these models are predicted much smaller yield flow than it is measured, which is natural, exactly for the reason which I described. We have strong contribution from hot stage, which still do not have large collective expansion, collective flow. Okay. There are two kinds of ideas to describe or to solve this puzzle, and we can split them into two classes. First is somehow reduce direct photon emission from the first hot quark gluon plasma stage. Okay, the idea is okay, is like that at the very beginning of the collision, the gluons should be produced more copiously, and as the gluons are chargeless, have no electric charge, they do not emit thermal photons, and only later, when these gluons transform into quarks, they start to emit thermal photons. And in this way, we somehow postpone thermal photon emission to the later stages. And example of such a approach is shown on the right. Indeed, with this approach, we can increase direct photon flow, and it gets closer to the data, but for the price of reduced spectrum or total yield of thermal photons, and discrepancy between measured and predicted direct photon yield still increases. And another kind of ideas is that we have some additional source of direct photons, which is not cylindrically symmetric, but has okay, emitted mostly in plane, and this can be a kind of synchrotron emission, or it was described in this paper of Shavkov and company. It is a transition between different levels of levels in strong magnetic field. So
You have a few minutes.
Okay, it is almost next to last slide. So and indeed, with this approach, we can predict a rather large asymmetry of photon yield at high PT. And what is even more exciting, that we will have negative flow of direct photons at very low PT, which is not predicted by any other model. But still, all these approaches have drawbacks that they cannot explain large values of triangular flow, which was also observed. And okay, so this not clear how to explain that direct photon triangular flow is more or less the same as triangular flow of final hadrons. Okay, that's it. What we would like to show. Instead of my conclusions, I would like to summarize questions which we have, which we would like to discuss. If we have some ideas, we can do it in discussion session. So I think I shouldn't read them.
Okay, Dmitri, thank you very much for the nice overview. Well, do we have some short questions, some urgent questions? Please raise your hand if you have some urgent questions. Otherwise, we can. Yes.
I have
yes, please.
the answer on one of the questions and short questions of author and short question of mine. Question was, when hydrodynamic description starts to work? General answer is the following. You have hydrodynamic formulation even for one quantum particle, so-called Madelung fluid or Bohm formulation hydrodynamics and other authors. So the difference between a quantum hydrodynamic in this sense and the classical hydrodynamics is the quantum corrections. When the quantum corrections is negligible, then you can say, oh, hydrodynamic description of our own is applied. So more general answer is every time and everywhere, just to test if the corrections are small. The question of mine is the following. You showed for the photons power-like behavior with parameter small n. I am curious, what is the values for that parameter n?
Okay, it is shown on the slide, on the plot, it is 125. And it's more or less the same as, okay, volume times square cubic root of this volume, which should be attributed to the extended time. So yes,
1 plus
125.
transverse in the power of n, power-like behavior, not exponentially decay.
It's written, alpha is written there.
Or you,
Dmitri, alpha is 1.25. That's, I think,
yes,
the question.
yes. If it is this is a question.
Yeah, I think that was the question. Okay, do we have some other questions? I don't see other questions. We're a little bit out of time. So, Dmitri, thank you very much again for your talk.